Ever wonder why things don't fly forever in a vacuum? Or why fish don't stop swimming? Get ready to laugh and learn about a paradox that stumped scientists for centuries. Today, we're diving into D'Alembert's paradox, a riddle that proves even brilliant minds can have a hilarious blind spot when it comes to fluids. Imagine an object, like a ball, moving through a perfect, invisible fluid. According to D'Alembert's calculations, this ball would feel absolutely no resistance, zero, nada, zilch. So let's set the scene. We have our imaginary fluid. It's incompressible, non-viscous, and irritational. Basically, it's the superhero of fluids, perfect and frictionless. Imagine a fluid so perfect, so frictionless, that if you pushed an object through it, it would just keep going, forever, like a perpetual motion machine of wetness. Now, put an object in this fluid, a boat, a fish, a rubber ducky. According to the math, it should move without any drag at all. It's like trying to swim in air, but even easier. And here's where the paradox kicks in. In the real world, things experience drag. Boats slow down, fish get tired, and rubber duckies eventually stop floating down the stream. D'Alembert's math said no drag, but our eyes say yes, drag. Why did his equations predict no drag? Because they were based on an ideal fluid, a theoretical concept that doesn't account for things like friction or turbulence. It's like designing a car that can fly, but forgetting about gravity. This paradox is funny because it highlights the gap between theoretical physics and real-world observations. It's like a super smart scientist saying, "My calculations say pigs can fly," and then a pig just walks away. The real world is messy, full of friction, viscosity, and all sorts of things that make fluids fluidy. But in D'Alembert's ideal world, everything was perfectly smooth and frictionless. The ideal fluid simply doesn't exist. It's a theoretical model that's great for simplifying problems, but not so great for predicting how a fish actually swims or a boat actually moves. So the simple explanation is this. D'Alembert's math was correct for his ideal fluid, but real fluids are not ideal. They have viscosity, they're sticky, and they create turbulence, swirly bits. It turns out, viscosity and turbulence are the unsung heroes of drag. Without them, we'd all be slipping and sliding around like we're on an infinite banana peel. Thank goodness for friction. These real-world factors cause a pressure difference around the object, which is what creates drag. So in summary, math good, assumptions bad, for real life. So D'Alembert's paradox isn't a flaw in math, but a hilarious lesson in the importance of choosing the right model for the right problem. Sometimes, reality is just too wonderfully messy for perfect equations. This paradox, while seemingly silly, actually taught us a lot about fluid dynamics. It pushed scientists to look beyond idealized models and delve into the complexities of real-world fluid behavior. It was a funny mistake that led to serious breakthroughs. And finally, the most important takeaway. Objects in fluids do get wet, and they do experience drag. So the next time you see a boat moving, remember D'Alembert's funny little paradox and the messy, wonderful world of physics. What are your thoughts on this paradox? Let me know in the comments. Don't be a paradox. Share the knowledge. Like, share, and subscribe for more videos that will mess with your head in the best way possible. And don't forget, from Beyonder.